So chapter 3 is all about motion in two dimensions. And we're going to tackle a fairly straightforward example of two-dimensional motion here. And that is motion on a ramp. And our strategy here is going to be actually somewhat similar to more complicated two-dimensional motion problems. But our number one strategy here is just going to be try and turn it into a one-dimensional problem. And so here I've got this scenario. I've got this block on a ramp, and it's at an angle theta. Right? And so, now if I was to imagine setting this situation up like this, then my block's obviously going to move in this direction if I just let go of it. It's on a frictionless ramp, right? So I just let go of that block, and it clearly accelerates down that slope. And so if we use just a standard coordinate system, then, sort of transposing this velocity here up into our coordinate system, you can see that we're going to have a component of the velocity that's in the y direction and a component of velocity that's in the x direction, aren't I? And so this is a two-dimensional problem. It's a little bit tricky, right? Gravity only pulls in the y direction, but then we've got this surface, and we haven't talked about forces, but it's kind of an ugly problem if we try and solve it with a standard coordinate system. But what is a coordinate system? Is that reality? Well, reality is we've got a block on a ramp, and if I let go of it, it's going to slide down the ramp. That's what's reality. The coordinate system is something that we impose on the problem. It's an abstraction that we impose on the problem in order to help us understand it, in order to help us solve it, in order to help communicate about it with other people. But it's not reality, right? Reality is the block rolls down the ramp, slides down the ramp. This business, that's something we kind of made up. So let's make it up different. Instead of picking a standard coordinate system, let's constrain the motion to one dimension, like this. I tilted my coordinate system. Presto! I've just turned a two-dimensional motion problem into a one-dimensional motion problem. Why? Because now the only motion is going to be in the x-axis. There's just no action at all in the y direction. So now everything is in the x-axis because I have tilted my coordinate system. Sometimes this freaks students out, because you're so used to seeing standard x and y, with x being horizontal and y being vertical. But again, there's no reason why it has to be like that. It just doesn't. Right? We can tip it if it makes the problem easier for us to solve. Because remember that the coordinate system is a tool that we invented to help us. Let's use the version that helps us the most, that makes the problem the easiest. So we're going to tilt it. And now all our action is in the x direction. Great. And so now we just have a one-dimensional motion problem. We can just use the big 5, which I realize that on my camera, because I kind of have a weak camera, this mostly looks like a blank piece of paper. This is the big 5 I'm showing you. Okay. So we're going to use our big 5, but we're just going to tilt our axes. No big deal. And so we just need, I'm going to give you this fact. We're not going to learn how to derive this until we get to chapter 5, I suppose. So for right now, you're just going to have to believe me that the acceleration on a ramp is g sine theta, which, kind of makes sense. If I just drop something like the screwdriver, ignoring air resistance, its acceleration will be negative 9.8, or another 9.8 meters per second squared. In other words, 9.8 meters per second squared in that direction. Well, if I put this screwdriver instead on a frictionless ramp, screwdriver, not frictionless, let's pretend it is, then it will accelerate down the ramp with an acceleration that is less than g, which kind of makes sense, right? It would be less than if I just dropped the screwdriver, right? Its acceleration is less on the ramp than it is if I just drop it. Kind of makes sense. It turns out that the acceleration of an object on a ramp is g sine theta. That's the magnitude. What is the direction? Down the ramp. So is that positive or negative? according to my coordinate system. According to my coordinate system, that is a positive acceleration. And remember, g is not negative 9.8. G is positive 9.8 meters per second squared. So my acceleration is down the ramp at g sine theta. Great, let's solve the problem. All right, here we go. I'm just going to read it real quickly and let it wash over me, and then I'm going to go back, read it more slowly, transfer stuff to my piece of paper. Ski jumpers go down a long slope on slippery skis, achieving a high speed before launching into the air. The in-run is essentially a ramp, which jumpers slide down to achieve the necessary speed. A particular ski jump has a ramp length of 120 meters, tipped at 21 degrees with respect to the horizontal. What is the highest speed that a jumper could reach at the bottom of such a ramp? Okay, so this is ramp motion. I'm thinking, ramp motion. I'm probably going to want to tilt my axes and turn it into a one-dimensional problem. That's what we just were talking about. Okay, let's go back and read it more slowly and see if we can't transfer some of this information to our piece of paper. Ski jumpers go down a long slope on slippery skis, achieving a high speed before launching into the air. I kind of knew that, bet you did too. The in-run is essentially a ramp which jumpers slide down to achieve the necessary speed. Okay, that's telling us we should treat this like a ramp problem, right? A particular ski jump has a ramp length of 120 meters tipped at 21 degrees with respect to the horizontal. Oh, okay, now we got some action that I should put on my paper. It says the ramp is 120 meters long. I'll draw my skier. We'll put him nice and small so I got room here to indicate that this is 120 meters. We should tilt our coordinate system, definitely. X and Y. Great. Now it's just a big 5 one-dimensional motion problem. Let's go ahead and make our list. All right, delta x. Do we know that? Yes, we do, 120 meters. V initial. Ooh, they didn't tell us, but I think we can assume they started from rest. V final, that's what we're looking for. It says maximum speed, that's what we're after. Delta t, didn't tell us, didn't ask. Ooh, that's a clue about what equation we might use. A, well, I just told you that the acceleration on a ramp is g sine theta. On a frictionless ramp, that's an important qualifier. The acceleration on a frictionless ramp is g sine theta. So there we go. And again, g is positive 9.8. Okay. You could run your calculator there. I prefer to leave my calculator running to the end. So let's look at our big 5. Which equation should we use? Well, you can pause the video, see which equation you would use. I feel like we should use equation number 3. So equation number 3 looks like this. We should plug in any zeros right away and then do our algebra. And now we should plug in our numbers. And now we can run our calculator. And we get 29 meters per second. Which, again, you can multiply by a little more than 2, and that's about 65 miles per hour. Okay, now we should assess. Does that make sense? Ski jumpers are going pretty fast at the end of this ramp, 120 meters. That's longer than a football field. Yeah, I think that seems like a reasonable number. I like it. Okay. One more comment on this tilting the axes. When should we do that? We're going to talk more about when we want to do that as we go through this class, but in general, what we want to do is we want to constrain our acceleration to one dimension, right? With a standard coordinate system, we would have had acceleration in the x and the y direction, which would have been tricky. Anytime we can constrain the acceleration to one dimension, we should. And I'm going to tell you that I will not ask you problems in this class where we cannot do that. There are situations where you can't, but not in this class. So in this class, you will always be able to have all of the acceleration in either x or y with an appropriately chosen coordinate system. And that's really the test about whether we should use a standard coordinate system or whether it's important for us to use a tilted coordinate system. If we can constrain the acceleration to one dimension, we really should. It makes the problem solving easier. It's not that you couldn't solve this with a standard XY coordinate system. It just would be much harder. I don't think I could do it in a 4x4 chalkboard. Right? I'm kind of getting tight over there as it is. So, anyhow, more on that as we go along.